Hi everyone, my name is Nadia Dachlythra and I'm a PhD student in Stockholm University, and I work on modeling optical systematics for current and next generation cosmic microwave background telescopes. My work has been mostly on various aspects and methods for beam characterization for the Simons Observatory telescope. However, this work can get rather technical, so I thought that for the scope of this conference, I would try to give a more pedagogical talk about beams instead. So why do we care about beams? How can improper beam modeling hurt the robustness of the results when it comes to CMB analysis? And what do we do about it as a community? The CMB community is very wide. I'm listing in this slide only some of the experiments that have mapped the microwave sky in the past. We have experiments coming up soon, such as the Simons Observatory telescopes, waiting to see their first light in 2024. And of course, we have very powerful upcoming missions in the future. So it's a great time to be involved in the field. And the reason that we put all this effort, of course, is because we can draw all sorts of information from the CMB. We can measure the cosmological parameters, we can get an idea about the initial conditions, number of effective spaces, the degree of primordial non-Gaussianity we should expect. And of course, there are degeneracies when we try to measure all these parameters, but by using together temperature and polarization of the CMB, we can break most of these degeneracies. And by using the polarization, we can get closer to another of scientific goals, which is to constrain the probability of gravitational waves being present at very early times, which will be a very strong probe of inflation. So of course, the community is very much after this specific scientific goal. Now, how do we do that? We know that CMB is polarized. We expect some degree of linear polarization due to Thomson scattering of the CMB photons by free electrons. And if we do our math there, we can actually break down the linearly polarized part of the CMB into a strong parity even and crop-free part, which we call the E-modes, and to a fainter parity odd and divergence-free part, which we refer to as the B-modes. And you can see them here projected as headless vectors on the celestial sphere by the WMAP collaboration. Now, the polarization anisotropies are much, much fainter than the temperature anisotropies, and so they're much harder to measure. However, there is one distinction that we can make and can help us, which is that the E-modes can be produced both by scalar and tensor perturbations, while the B-modes can only be sourced by tensor perturbations. And given that inflationary gravitational waves are basically perturbations, tensor perturbations of the metric, what we can do is we can try to estimate how much do the scalar and the tensor perturbations contribute separately to the linear polarization of the CMB. So we craft this parameter called tensor-to-scalar ratio, denoted here by R, which is exactly the ratio of the tensor to scalar perturbations amplitude. And of course, we have already set constraints to this parameter. The latest ones come from the combined data of Bicep, Keck, and Planck collaborations, setting an upper limit to 0.032 at a 95% confidence level. And it's quite common that the CMB experiments set their scientific goals in terms of the accuracy within which they want to constrain this parameter. So the Simons Observatory telescopes, for example, are looking at constraining R with a sigma less or equal to 0.003, while the future ground-based S4 and JAXA's new class mission satellite called LIGHTBIRD, they are aiming at a 0.003 detection with a statistical uncertainty of only 1/3 of the already optimistic goals set by the Simons Observatory telescopes. So we're talking about very, very tight constraints, very ambitious goals. And to achieve these ambitious goals, we need mainly two things. We need to have good frequency coverage, and this will allow us to separate the foregrounds, the very strongly emitting foregrounds, from the CMB. And this is because the foregrounds are actually very much frequency dependent, while the CMB follows a black body distribution. So the more frequency coverage we have, the more accurately we can model the spectral energy distribution of all our sky components, and so separate them. And the other thing that we need is to have very, very good knowledge of our instrument. A great category for our telescopes of instrument systematics are the optical systematics, and a very great category of the optical systematics are the beam systematics. And this is basically my opening statement for starting to ramble about beams. So the time is finally here. We need to understand what we mean when we talk about the beam, the point spread function of our instrument. So by that, we simply refer to the instrument's response to a point source. And this is what defines the resolution of our instrument. So what is the minimum distance between two similar objects for our instrument to actually be able to perceive these objects as distinct objects? And the resolution of the instrument is very much limited by diffraction. Diffraction occurs because Well, the light waves, when they propagate, they don't really propagate as straight lines rather than spherical wavelets. Sorry. So when they encounter a slit or an aperture, they're going to interfere in constructive or destructive ways, and they will form thus complex patterns. Those patterns will depend on the shape of the aperture, of course. If you have a circular aperture, is the pattern that you're seeing here on the left, which we call an airy pattern. And this is comprised of a very bright central maximum, which we call the main lobe of the beam, surrounded by concentric light rings, which we call the beam side lobes. And you can see them here on the right side projected in 1D. This blue line is the main lobe. And to the best of my drawing abilities in Google Slides, those red lines are the near beam side lobes. Why do we care? So if we don't properly model our beams, we might encounter all sorts of problems in the analysis. First of all, for the side lobes, if we have power that we haven't properly modeled, accounted for, far away from the center of our beam, we might end up picking unwanted parts of the sky, the strongly emitting galaxy, for example. And even if we mask the galaxy afterwards in the analysis, then we will still have contaminated signal. And this can be rather problematic. But also, if we have, for ground-based telescopes, if we have power very far away from the center of our beam, we will actually also start picking up emission from the ground. And of course, we baffle our telescopes in this case, but we might still end up with some amount of ground pickup. The beam can also be asymmetrical. Of course, when we design a telescope, we have softwares to optimize the optical setup in order to avoid problems before they get created, so we don't have to solve them afterwards. But there are cases that even if we have a very symmetric optical setup, a radially symmetric optical setup, then when deploying the telescope or in the analysis, we might want or need to turn off, let's say, 10% of the edge detectors on the one side of our perfectly symmetrical focal plane. And that will make the beam inherit some degree of ellipticity, which will be, we will need to account for later, since we have set such ambitious goals on constraining our measured parameters. And of course, there is the dreadful case that the non-idealities of our beam just go strolling around the telescope and become buddy-buddy with non-idealities of other components of the telescope. If we have a half-wave plate, for example, which is a very common polarization modulator used in CMB telescopes, then the non-idealities of the half-wave plate will go and couple to the non-idealities of the beam. And this is really not a trivial problem to solve, which is something that we have to find out the hard way in a work that we did a couple of years ago. So we need to model our beam properly. We need to define the beam transfer function, as we call it. And this transfer function will look a little bit like this for the case of the ACT telescope, for example, as it was defined from Uranus simulations not so long ago by this work in Lugo et al. And if we were to put this in a mathematical framework to see how the transfer function really impacts our measured spectra, we just made this equation here on the left. So on the left side of the equation, we have the measured spectra from the telescope, and those are linked to the true spectra by a matrix, sorry, I just wanted to highlight it, by a matrix that gives us an idea about the deviation from the basis orthogonality due to cut sky effects, because of course sometimes we're not able to observe the full sky. Then we need to have some information about the filtering, denoted here by this F above, all the filtering that we did to the data for noise mitigation and so on. And then what we are talking about in this case, the beam transfer function squared, in which case is referred to as the window function that acts directly on the power spectrum. And we need a noise term to complete the formulation. So it's really, really important to recover to the best of our abilities the beam transfer function. And of course, we're not ignorant towards that. Beam calibration is always part of the process when we deploy a telescope, and way before that when we do our forecasting. And we will do that on the field. We will use astrophysical sources, of course. Planets are very good candidates. When we cannot do that or we have different calibration needs, we will employ artificial sources. But again, we need to have some level of preparation in the lab before that. We do near-field measurements, and lately, holography is also becoming very, very popular. So if we were to look at these categories one by one, planets are always used for beam calibration. They're really good candidates, bright point sources in the sky. The moon has also been used here is a reference to the class calibration. It's really, really good for calibrating also the far side lobes of the beam. However, there is a problem that because it's so bright, we might actually risk saturating our detectors. So we don't want that, of course. Now, there is a downside, which is that when we're observing from the ground, it gets harder to observe the planets whenever we want. Sometimes during some months, perhaps the planets are not rising high enough in elevation. And then again, not all planets will going to be bright enough to calibrate all of the same telescopes. And there is also the problem of, how do we calibrate the polarized response of our instrument? The planets are fundamentally unpolarized, and they have an upper polarization fraction, I think, up to 3–4%, as measured by the Planck collaboration. However, we do have one good candidate, and this is Crab Nebula Tau A, that has been used in the past to calibrate the polarization and the polarized response of our telescope release. So we do have some limitations, and sometimes we need to come up with alternative solutions to go through the calibration. So we start looking into man-made sources. These sources need to be propagated to a large enough distance from a telescope that depends on the instrument characteristics and the wavelength of the radiation that we want to look at. We can mount the source on some tall structure, like happened for BICEP. We can have a source in a balloon. In the case of Boomerang, there was this source in the balloon which was flashed, basically during fixed time intervals. And what we're actively looking at as well is mounting sources on drones, and another possible solution for the future that has been suggested is to have a spaceborne open access calibration source for suborbital and ground experiments. The good thing with that is that we're not subject anymore to availability issues. We can have as many measurements as we want. We can tune the source to achieve a higher signal-to-noise ratio as compared to planets in order to satisfy our beam calibration requirements. And we can also make the source polarized. For example, putting a polarized grid in front of the source, which solves the problem of the limited sources, the limited natural astrophysical sources that there are out there to calibrate our instrument. The limited polarized astrophysical sources that are out there to calibrate our instrument. And I would like to show here just as a reference, this refers to the case where we're looking at how we would calibrate our beam for the small aperture telescopes of the Simons Observatory. It's some work that we did in the past. And we were looking at how much the signal-to-noise ratio that we could achieve would be in the case of some bright planets. We have looked at 3 bright planets here, and the source that was mounted on a drone as an alternative solution. And we can see that the source on the drone has actually much higher signal-to-noise ratio, and it's also flatter over the range of frequencies that we want to look at. So this is important. And I wanted to mention here that this has been estimated only for the white noise levels, and 1 pixel at a time and 1 second integration time. So it's a pure comparison basically of the power between the different sources. But of course, artificial sources come with limitations of their own, technical limitations. If we have a drone, for example, there's a specific amount of time that we can keep it stable, and we need to have it powered all the time. And this poses a natural trade-off that is always there between astrophysical and artificial sources. Now, when we get in the lab, we get the chance of probing the instrument itself, the optical setup itself, a little bit more immediately. When we do measurements at the aperture plane, near-field measurements, we use thermal sources, and those have a black body emission spectrum. So we get amplitude, but we don't get phase information. But those measurements are actually quite useful, as they can track internal reflections, and we can use them also as future reference for when it comes to optics and detectors fabrication. And you can see here on the right, I have these near-field maps from the optical characterization for the BICEP cake instrument. In the left column, we see the near-field maps for a central pixel. In the right column, it's for an edge pixel on the focal plane. And you can see here there is a small bright pixel, and this is an internal reflection of the main beam, of low amplitude, of course, but this is what we call a ghost. And also on the right side, you can see that for the edge detectors, The near-field maps are more asymmetrical. There is asymmetrical illumination of the aperture. And this will naturally translate to some degree of ellipticity when we propagate to the far field, but it will be a moderate effect. So here it's so much easier to see and track. So near-field measurements are very, very useful. One other thing that we can do, and has been done recently for the Large Aperture Telescope of the Simons Observatory, is go to holography. So if we have a coherent source, we can do near-field measurements for single frequencies, for a number of single frequencies, for the frequency band that we're looking at. And this, of course, will take some more time. But then we get to have amplitude and phase information. And we want to propagate that into the far field. So in that case, we can have simulations of a distant point source, a very distant point source, propagating through a virtual telescope, and we can produce the fields on the measurement plane. And then we can take these fields and we multiply them with the near field maps that we have, and we integrate over the focal plane, the full focal plane. And then we take our telescope and we rotate in azimuth and elevation and repeat this process until we get a full beam far field map. And this is what you're seeing here on the right side. This picture is from the paper of Chesmore et al., 2022, that they have the far field maps for 2 frequency bands centered at 90 and 150 gigahertz, both in the XY coordinates, but also radially beamed and compared to this black dashed line simulations. And you can see that the results are quite accurate. It gives us power. So we have the measurements in the near field, we have the measurements in the far field. We do our simulations for astrophysical sources, we employ artificial sources. We basically try to tackle the problem all together in many ways, because beam calibration is actually quite hard to achieve in practice. And as the instruments get more robust, we have more tight constraints on our endgame, which is in our case, the tensor-to-scalar ratio. So we need to come up with the smallest error possible from the beam calibration to fit in the already very optimistic and ambitious error budget that we make for our instruments. And since this was at least I tried for this to be a more pedagogical talk, there is no conclusion per se, but I hope that by now I have convinced you that beams are really important for CMB analysis, and even potentially that the analysis is kind of cool. And I'm really looking forward to discussing more if you have any questions during the live sessions. So thank you very much for watching the talk, and I look forward to discussing more. Bye.